Hello, in this video we're going to solve a math question, and this is on vectors and planes. So we need to find the minimum distance between the point A, which is negative 5 comma 0 comma 1, and the plane of this, r equals whatever, in the form a square root b, where a and b are both integers. Okay, how do we approach this question? I guess we can start by just drawing the whole thing out. So there's a plane somewhere, and there's a point somewhere where it's negative 5, 0, comma 1. And this equation is, the equation of the plane is r. Okay, so the minimum distance between the point and the plane is going to be the normal of the, it's going to be the normal of the plane to the point. And I will maybe try to illustrate this on Desmos later, at the end of the question. But it's the normal. And to find the normal of the plane, we can do the vector product between between these, the direction vectors. So let's name the normal line or vector n, and let's do the vector product. So negative 1, 1, 3 times negative 3, negative 4, and 2. Yeah, okay. So there is a formula for this. Right here. It's quite simple, or it's sort of like a pattern once you practice it a lot of times, but essentially, like, this is 1, 2, and 3, and this is 1, 2, and 3, and the x is going to be 1 times 2, so 2 minus 3 times 2, which is negative 12. And then the x coordinate is going to be 3 times 1, negative 9, minus 1 times 3, which is negative 2. And the z is going to be 1 times 2, which is 4, minus 2 times 1, which is negative 3. Okay. So it's going to be 2 plus 12, which is 14, negative 9 plus 2, which is negative 7, and 4 plus 3, which is 7. Okay. I guess a plane is not just finite, so it would be like this maybe, but even bigger and infinite. And essentially this normal would be, actually we can simplify this even further, because this would be, the ratio would be 2, negative 1, and 1 if we divide everything by 7. So the direction is going to be, okay, this is in the way. Okay, never mind. It's going to be like this, essentially. It's touching the plane here, and it's touching the point here, because we want the minimum distance. And the normal is the minimum distance. So, and this is the direction vector of the normal, so we have that now. Okay. Now what do we do? Okay, we can write, or we can actually get the equation of the plane. I think that would be helpful. So the equation of the plane we can label as pi equals, so the normal is actually the numerator of the Cartesian form of the plane. So it's going to be 2x minus y plus c equals a constant. And to get the constant, we need a point on the plane, and we're given that here, and we just sub it in. So what is this? 1, 1, 2. Okay. So 2 times 1 is 2 minus 1 plus 2 equals the constant. And 2 minus 1 plus 2, that's 3. And this is equal to the constant. So the final equation of the plane is 2x minus y plus c equals 3. Okay. Don't think we can do anything with it right now. But we can also get the equation of the line because we have the direction vector, which is the normal, and the point. So we can write this in matrix form. So we can label the line as L equals the point, which is -5, 0, 1, plus, let's see, we can just, label that as S instead of lambda because it's already used here. And the direction vector is 2, -1, 1. Okay. And we can put this in parametric form because we want the intersection here. We want that intersection. So we can use the distance formula because we'll have 2 points and then we'll answer the question. But to get that intersection, we need to sub this line into the Cartesian, into the plane so we can get the intersection. But first we need to convert this into parametric form. So x equals -5 plus 2s, y equals -s, z equals 1 plus s. Okay, and then we can sub this in here. So equals 2 -5 plus 2s minus -s plus 1 plus s. Oops, why did I put a bracket? Equals s. Oh, what am I saying? Yeah, equals 3, the constant. Okay. Now we just solve for s, and then we can substitute s back in the line formula so we can get the coordinates of the intersection. Yeah. Okay, so this is -10 plus 4s plus s plus 1 plus s equals 3, and 4s plus s plus s, that's 6s. Okay. We move -1 over here, so that's a 2, and that's removed. And then this, we add 10 to each side, so that's removed, and that's a 12. Okay, so that's a 12. Okay, good. So s is 2. Okay, now we can substitute s back in here, and s is 2, so -5 plus 4, that's -1, -2, and 3. Okay, so the intersection is -1, -2, and 3. Okay, now let's put it back in the visualization. -1, -2, 3. And yeah, that's very good because now we have 2 coordinates and we just need to use the distance formula. So the distance between the x coordinates, that's just 4. So 4 squared plus 2 squared and 3, not 3, distance, yeah. 2 squared and then square root everything. D equals 16 plus 4 plus 4 equals 24. The square root of 24. And then, what is it? It wanted it in, this, so we can simplify this even further. What is 24? 6 times 4. Okay, yeah. And then 4 can be moved out. Okay. And yeah, I think pretty confident with this. What are the units? There's no units. Okay, well, I'm just writing units. Okay, and that's the final answer. Okay, so like I said at the start of the video, I would try to put this on Desmos 3D so you guys can see. So this is the Cartesian equation of the plane, which is in red. This is the point A that we were given. This is the Cartesian equation of the normal line that crosses through the intersection that we calculated for. And yeah, this is what it looks like. Yeah, it looks pretty normal. Yeah, this is making a 90-degree angle, which is the normal, and this looks like the shortest intersection between, okay, let's just remove this and this. Yeah, so the shortest distance wouldn't be to here. It would intuitively, based off this diagram, this illustration, be a straight line just there, which is the normal here. And that's the intersection. And yeah, the distance is, like we calculated, 2 square root 6 units. And yeah, that's it for this question. Thank you.